Submarine.
A submarine is a watercraft capable of independent operation underwater. It differs from a submersible, which has more limited underwater capability. The term most commonly refers to a large, crewed, autonomous vessel. It is also sometimes used historically or colloquially to refer to remotely operated vehicles and robots, as well as medium-sized or smaller vessels, such as the midget submarine and the wet sub. Used as an adjective in phrases such as submarine cable, submarine means under the sea. The noun submarine evolved as a shortened form of submarine boat. For reasons of naval tradition, submarines are usually referred to as boats rather than as ships, regardless of their size. Although experimental submarines had been built before, submarine design took off during the 19th century, and they were adopted by several navies. Submarines were first widely used during World War I, 1914 to 1918, and now figure in many large navies. Military usage includes attacking enemy surface ships, merchant and military, submarines, aircraft carrier protection, blockade running, ballistic missile submarines as part of a nuclear strike force, reconnaissance, conventional land attack, for example using a cruise missile, and covert insertion of special forces. Civilian uses for submarines include marine science, salvage, exploration and facility inspection maintenance. Submarines can also be modified to perform more specialized functions such as search and rescue missions or undersea cable repair. Submarines are also used in tourism, and for undersea archaeology. Most large submarines consist of a cylindrical body with hemispherical, and/or conical, ends and a vertical structure, usually located amidships, which houses communications and sensing devices as well as periscopes. In modern submarines, this structure is the sail in American usage, and fin in European usage. A conning tower was a feature of earlier designs, a separate pressure hull above the main body of the boat that allowed the use of shorter periscopes. There is a propeller, or pump jet, at the rear, and various hydrodynamic control fins. Smaller, deep-diving and specialty submarines may deviate significantly from this traditional layout. Submarines change the amount of water and air in their ballast tanks to decrease buoyancy for submerging or increase it for surfacing. Submarines have one of the widest ranges of types and capabilities of any vessel. They range from small autonomous examples and one- or two-person vessels that operate for a few hours, to vessels that can remain submerged for 6 months, such as the Russian Typhoon class, the biggest submarines ever built. Submarines can work at greater depths than are survivable or practical for human divers. Modern deep-diving submarines derive from the bathyscaphe, which in turn evolved from the diving bell.
History. Early submersibles.
The first submersible of whose construction we have reliable information was built in 1620 by Cornelius Drebbel, a Dutchman in the service of James I of England. It was created to the standards of the design outlined by English mathematician William Bourne. It was propelled by means of oars. The precise nature of the submarine type is a matter of some controversy. Some claim that it was merely a bell towed by a boat. By the mid-18th century, over a dozen patents for submarine submersible boats had been granted in England. In 1747, Nathaniel Symonds patented and built the first known working example of the use of a ballast tank for submersion. His design used leather bags that could fill with water to submerge the craft. A mechanism was used to twist the water out of the bags and cause the boat to resurface. In 1749 the Gentleman's Magazine reported that a similar design had initially been proposed by Giovanni Borelli in 1680. By this point of development, further improvement in design necessarily stagnated for over a century, until new industrial technologies for propulsion and stability could be applied. The first military submarine was the Turtle, 1775, a hand-powered acorn-shaped device designed by the American David Bushnell to accommodate a single person. It was the first verified submarine capable of independent underwater operation and movement, and the first to use screws for propulsion. In 1800, France built a human-powered submarine designed by American Robert Fulton, the Nautilus. The French eventually gave up on the experiment in 1804, as did the British when they later considered Fulton's submarine design. In 1864, the fourth year of the American Civil War, the Confederate Navy's H.L. Hunley became the first military submarine to successfully sink an enemy vessel. In the aftermath of its successful attack against an American Union ship, the Hunley also sank, possibly due to its being too close to its own exploding torpedo.
Mechanical power.
The first submarine not relying on human power for propulsion was the French Plongeur, diver, launched in 1863, and using compressed air at 180 psi, 1241 kilopascals. The first air-independent and combustion-powered submarine was the Ictinio II, designed by the Spanish intellectual, artist and engineer Narcí Manchurial. Launched in Barcelona in 1864, it was originally human-powered, but in 1867 Manchurial invented an air-independent engine to power it underwater. The 14 meters, 46 feet, long craft was designed for a crew of 2, performed dives of 30 m, 98 feet, and remained underwater for 2 hours. Both the Ictinio I and II were double-hulled vessels that solved pressure and buoyancy control problems that had troubled and limited the functionality of earlier submarines. The submarine became a potentially viable weapon with the development of the Whitehead torpedo, the first practical self-propelled or locomotive torpedo. The spar torpedo that had been developed earlier by the Confederate Navy was considered to be impracticable, as it was believed to have sunk both its intended target, and probably the H.L. Hunley, the submarine that deployed it. The Whitehead torpedo was designed in 1866 by British engineer Robert Whitehead. His mined ship was an 11-foot-long, 14-inch diameter torpedo propelled by compressed air and carried an explosive warhead. The device had a speed of 7 knots, 13 km per hour, and it could hit a target 700 yards, 640 m, away. Discussions between the English clergyman and inventor George Garrett and the Swedish industrialist Thorsten Nordenfeldt led to the first practical steam-powered submarines, armed with torpedoes and ready for military use. The first was the Nordenfeldt I, a 56-ton, 19.5-meter, 64 feet, vessel similar to Garrett's ill-fated Resurgam, 1879, with a range of 240 kilometers, 150 miles, 130 nanometers, armed with a single torpedo, in 1885. Like Resurgam, Nordenfeldt I operated on the surface by steam, then shut down its engine to dive. While submerged, the submarine released pressure generated when the engine was running on the surface to provide propulsion for some distance underwater. Greece, fearful of the return of the Ottomans, purchased it. Nordenfeldt then built Nordenfeldt II, Abdul Hamid, in 1886 and Nordenfeldt III, Abdul Mesud, in 1887, a pair of 30-meter, 100 feet, submarines with twin torpedo tubes, for the Ottoman Navy. Abdul Hamid became the first submarine in history to fire a torpedo submerged. Nordenfeldt's efforts culminated in 1887 with Nordenfeldt IV, which had twin motors and twin torpedoes. It was sold to the Russians, but proved unstable, ran aground, and was scrapped. A reliable means of propulsion for the submerged vessel was only made possible in the 1880s with the advent of the necessary electric battery technology. The first electrically powered boats were built by James Franklin Waddington in England, Dupuy de Lome and Gustave Zede in France and Isaac Perel in Spain. Waddington's porpoise was similar in size to the Resurgam and its propulsion system consisted of 45 accumulator cells with a capacity of 660 ampere-hours each. These were coupled in series to a motor driving a propeller at about 750 rpms, giving the ship a sustained speed of 8 miles per hour for at least 8 hours. The boat was armed with 2 externally mounted torpedoes as well as a mine torpedo that could be detonated electronically. Although the boat performed well at trials, Waddington was unable to attract further contracts and went bankrupt. The Spanish Peril submarine was launched in 1888, and had 3 Schwarzkopf torpedoes 14 in, 360 mm, and one torpedo tube in bow. Newer systems, hull shape, propeller, and cruciform external controls anticipating much later designs. Peril was an all-electrical powered submarine. After 2 years of trials, the project was scrapped by naval officialdom, who cited, among other reasons, concerns over the range permitted by its batteries. The Gymnot was launched by the French Navy in the same year. Gymnot was also an electrically powered and fully functional military submarine. It completed over 2,000 successful dives using a 204-cell battery. Although the Gymnot was scrapped for its limited range, its side hydroplanes became the standard for future submarine designs.
The modern submarine.
Submarines were not put into service for any widespread or routine use by navies until the early 1900s. The turn of the century marked a pivotal time in submarine development, and a number of important technologies appeared. A number of nations built and used submarines. Diesel-electric propulsion became the dominant power system, and equipment such as the periscope became standardized. Countries conducted many experiments on effective tactics and weapons for submarines, which led to their large impact in World War I. The Irish inventor John Philip Holland built a model submarine in 1876 and a full-scale one in 1878, followed by a number of unsuccessful ones. In 1896 he designed the Holland Type 6 submarine. This vessel made use of internal combustion engine power on the surface and electric battery power for submerged operations. Launched on May 17, 1897 at Navy Lieutenant Lewis Nixon's Crescent Shipyard in Elizabeth, New Jersey, the Holland 6 was purchased by the United States Navy on April 11, 1900, becoming the United States Navy's first commissioned submarine and renamed USS Holland. Commissioned in June 1900, the French steam and electric naval employed the now typical double-hull design, with a pressure hull inside the outer shell. These 200-ton ships had a range of over 100 miles, 160 kilometers, underwater. The French submarine Aigrette in 1904 further improved the concept by using a diesel rather than a gasoline engine for surface power. Large numbers of these submarines were built, with 76 completed before 1914. The Royal Navy commissioned 5 Holland-class submarines from Vickers, Barrow and Furness, under license from the Holland Torpedo Boat Company during the years 1901 to 1903. Construction of the boats took longer than anticipated, with the first only ready for a diving trial at sea on April 6, 1902. Although the design had been purchased entire from the U.S. company, the actual design used was an untested improved version of the original Holland design using a new 180-horsepower petrol engine. These types of submarines were first used during the Russo-Japanese War of 1904 May. Due to the blockade at Port Arthur, the Russians sent their submarines to Vladivostok, where by January 1, 1905 there were 7 boats, enough to create the world's first operational submarine fleet. The new submarine fleet sent out its first patrol on February 14, usually lasting for about 24 hours. The first confrontation with Japanese warships occurred on April 29, 1905 when the Russian submarine Somme was fired upon by Japanese torpedo boats, but then withdrew.
World War I.
Military submarines first made a significant impact in World War I. Forces such as the U-boats of Germany saw action in the First Battle of the Atlantic, and were responsible for the sinking of RMS Lusitania, which was sunk as a result of unrestricted submarine warfare and is often cited among the reasons for the entry of the United States into the war. At the very outbreak of war, Germany had only 20 submarines immediately available for combat, although these included vessels of the diesel-engined U-19 class with a range, 5,000 miles, and speed, 8 knots, to operate effectively around the entire British coast. By contrast, the Royal Navy had a total of 74 submarines, though of mixed effectiveness. In August 1914, a flotilla of 10 U-boats sailed from their base in Heligoland to attack Royal Navy warships in the North Sea in the first submarine war patrol in history. The U-boats' ability to function as practical war machines relied on new tactics, their numbers, and submarine technologies such as combination diesel-electric power system developed in the preceding years. More submersibles than true submarines, U-boats operated primarily on the surface using regular engines, submerging occasionally to attack under battery power. They were roughly triangular in cross-section, with a distinct keel to control rolling while surfaced, and a distinct bow. During World War I, more than 5,000 Allied ships were sunk by U-boats.
World War II.
During World War II, Germany used submarines to devastating effect in the Second Battle of the Atlantic, where it attempted to cut Britain's supply routes by sinking more merchant ships than Britain could replace. Shipping was vital to supply Britain's population with food, industry with raw material, and armed forces with fuel and armaments. While U-boats destroyed a significant number of ships, the strategy ultimately failed. Although the U-boats had been updated in the interwar years, the major innovation was improved communications, encrypted using the famous Enigma cipher machine. This allowed for mass attack tactics, Rodeltaktik, commonly known as Wolfpack, but was also ultimately the U-boat's downfall. By the end of the war, almost 3,000 Allied ships, 175 warships, 2,825 merchantmen, were sunk by U-boats. The Imperial Japanese Navy operated the most varied fleet of submarines of any navy, including Coit and crude torpedoes, midget submarines, Type A Kohayotki and Kari classes, medium-range submarines, purpose-built supply submarines and long-range fleet submarines. They also had submarines with the highest submerged speeds during World War II, I-201 class submarines, and submarines that could carry multiple aircraft, I-400 class submarines. They were also equipped with one of the most advanced torpedoes of the conflict, the oxygen-propelled Type 95. Nevertheless, despite their technical prowess, Japan had chosen to utilize its submarines for fleet warfare, and consequently were relatively unsuccessful, as warships were fast, maneuverable and well-defended compared to merchant ships. The submarine force was the most effective anti-ship and anti-submarine weapon in the entire American arsenal. Submarines, though only about 2% of the U.S. Navy, destroyed over 30% of the Japanese Navy, including 8 aircraft carriers, 1 battleship and 11 cruisers. U.S. submarines also destroyed over 60% of the Japanese merchant fleet, crippling Japan's ability to supply its military forces and industrial war effort. Allied submarines in the Pacific War destroyed more Japanese shipping than all other weapons combined. This feat was considerably aided by the Imperial Japanese Navy's failure to provide adequate escort forces for the nation's merchant fleet. During World War II, 314 submarines served in the United States Navy, of which nearly 260 were deployed to the Pacific. On December 7, 1941, 111 boats were in commission. 203 submarines from the Gato, Belay, and Tench classes were commissioned during the war. During the war, 52 U.S. submarines were lost to all causes, with 48 directly due to hostilities. U.S. submarines sank 1,560 enemy vessels, a total tonnage of 5.3 million tons, 55% of the total sunk. The Royal Navy submarine service was used primarily in the classic British blockade role. Its major operating areas were around Norway, in the Mediterranean, against the Axis supply routes to North Africa, and in the Far East. In that war, British submarines sank 2 million tons of enemy shipping and 57 major warships, the latter including 35 submarines. Among these is the only documented instance of a submarine sinking another submarine while both were submerged. This occurred when HMS Ventura engaged the U-864. The Ventura crew manually computed a successful firing solution against a three-dimensionally maneuvering target using techniques which became the basis of modern torpedo computer targeting systems. 74 British submarines were lost, the majority, 42, in the Mediterranean.
Modern military models.
The first launch of a cruise missile, SSBN-8 Regulus, from a submarine occurred in July 1953, from the deck of USS Tunney, a World War II fleet boat modified to carry this missile with a nuclear warhead. Tunney and its sister boat, Barbaro, were the United States' first nuclear deterrent patrol submarines. In the 1950s, nuclear power partially replaced diesel-electric propulsion. Equipment was also developed to extract oxygen from seawater. These two innovations gave submarines the ability to remain submerged for weeks or months. Most of the naval submarines built since that time in the United States, the Soviet Union, Russia, Britain and France have been powered by nuclear reactors. In 1959 to 1960, the first ballistic missile submarines were put into service by both the United States, George Washington class, and the Soviet Union, Hotel class, as part of the Cold War nuclear deterrent strategy. During the Cold War, the United States and the Soviet Union maintained large submarine fleets that engaged in cat-and-mouse games. The Soviet Union suffered the loss of at least 4 submarines during this period. K-129 was lost in 1968, which the CIA attempted to retrieve from the ocean floor with the Howard Hughes-designed ship Glomar Explorer, K-8 in 1970, K-219 in 1986, and Komsomolets in 1989, which held a depth record among military submarines, 1,000 m. Many other Soviet subs, such as K-19, the first Soviet nuclear submarine, and the first Soviet sub to reach the North Pole, were badly damaged by fire or radiation leaks. The U.S. lost 2 nuclear submarines during this time, USS Thresher due to equipment failure during a test dive while at its operational limit, and USS Scorpion due to unknown causes. During the Indo-Pakistani War of 1971, the Pakistan Navy's hangar sank the Indian frigate INS Kukri. This was the first kill by a submarine since World War II. In 1971, the Ghazi, a Tench-class submarine on loan to Pakistan from the U.S., was sunk in the Indo-Pakistani War. It was the first submarine war loss since World War II. In 1982 during the Falklands War, the Argentine cruiser General Belgrano was sunk by the British submarine HMS Conqueror, the first sinking by a nuclear-powered submarine in war.
Usage. Military.
Before and during World War II, the primary role of the submarine was anti-surface ship warfare. Submarines would attack either on the surface or submerged, using torpedoes or, on the surface, deck guns. They were particularly effective in sinking Allied transatlantic shipping in both World Wars, and in disrupting Japanese supply routes and naval operations in the Pacific in World War II. Mine-laying submarines were developed in the early part of the 20th century. The facility was used in both World Wars. Submarines were also used for inserting and removing covert agents and military forces, for intelligence gathering, and to rescue aircrew during air attacks on islands, where the airmen would be told of safe places to crash land so the submarines could rescue them. Submarines could carry cargo through hostile waters or act as supply vessels for other submarines. Submarines could usually locate and attack other submarines only on the surface, although HMS Venture managed to sink U-864 with a 4-torpedo spread while both were submerged. The British developed a specialised anti-submarine submarine in WWI, the U-class. After WWII, with the development of the homing torpedo, better sonar systems, and nuclear propulsion, submarines also became able to hunt each other effectively. The development of submarine-launched ballistic missile and submarine-launched cruise missiles gave submarines a substantial and long-range ability to attack both land and sea targets with a variety of weapons ranging from cluster bombs to nuclear weapons. The primary defense of a submarine lies in its ability to remain concealed in the depths of the ocean. Early submarines could be detected by the sound they made. Water is an excellent conductor of sound, much better than air, and submarines can detect and track comparatively noisy surface ships from long distances. Modern submarines are built with an emphasis on stealth. Advanced propeller designs, extensive sound-reducing insulation, and special machinery help a submarine remain as quiet as ambient ocean noise, making them difficult to detect. It takes specialized technology to find and attack modern submarines. Active sonar uses the reflection of sound emitted from the search equipment to detect submarines. It has been used since WWII by surface ships, submarines and aircraft, via dropped buoys and helicopter dipping arrays, but it gives away the position of the emitter and is susceptible to countermeasures. A concealed military submarine is a real threat, and because of his stealth, can force an enemy navy to waste resources searching large areas of ocean and protecting ships against attack. This advantage was vividly demonstrated in the 1982 Falklands War when the British nuclear-powered submarine HMS Conqueror sank the Argentine cruiser General Belgrano. After the sinking, the Argentine Navy recognized that they had no effective defense against submarine attack, and the Argentine surface fleet withdrew to port for the remainder of the war, though an Argentine submarine remained at sea.
Civil.
Although the majority of the world's submarines are military, there are some civil submarines. They have a variety of uses, including tourism, exploration, oil and gas platform inspections, and pipeline surveys. The first tourist submarine was launched in 1985, and by 1997 there were 45 of them operating around the world. Submarines with a crush depth in the range of 400 to 500 feet, 120 to 150 m, are operated in several areas worldwide, typically with bottom depths around 100 to 120 feet, 30 to 37 m, with a carrying capacity of 50 to 100 passengers. In a typical operation, for example, Atlantis submarines, a surface vessel carries passengers to an offshore operating area, where passengers are exchanged with those of the submarine. The submarine then visits underwater points of interests, typically either natural or artificial reef structures. To surface safely without danger of collision, the location of the submarine is marked with an air release and movement to the surface is coordinated by an observer and a support craft. A recent development is the deployment of so-called narco submarines by South American drug smugglers to evade law enforcement detection. Although they occasionally deploy true submarines, most are self-propelled semi-submersibles, where a portion of the craft remains above water at all times. In September 2011, Colombian authorities seized a 16-meter-long submersible that could hold a crew of 5, costing about $2 million. The vessel belonged to FARC rebels and had the capacity to carry at least 7 tons of drugs.
Polar operations.
1903, Simon Lake Submarine Protector surfaced through ice off Newport, Rhode Island. 1930, USS 012 operated under ice near Spitsbergen. 1937, Soviet submarine Krasnogvadiets operated under ice in the Denmark Strait. 1941-45, German U-boats operated under ice from the Barents Sea to the Laptev Sea. 1946, USS Achil used upward-beamed fathometer in Operation Nanook in the Davis Strait. 1946-47, USS Senate used under ice sonar in Operation High Jump in the Antarctic. 1947, USS Boarfish used upward-beamed echo sounder under pack ice in the Chukai Sea. 1948, USS Carp developed techniques for making vertical ascents and descents through polynyas in the Chukai Sea. 1952, USS Redfish used an expanded upward-beamed sounder array in the Beaufort Sea. 1957, USS Nautilus reached 87 degrees north near Spitsbergen. August 3, 1958, Nautilus used an inertial navigation system to reach the North Pole. March 17, 1959, USS Skate surfaced through the ice at the North Pole. 1960, USS Argo transited 900 miles, 1,400 kilometers, under ice over the shallow, 125 to 180 feet or 38 to 55 meters deep, Bering Chukai Shelf. 1960, USS Seadragon transited the Northwest Passage under ice. 1962, Soviet November-class submarine K-3 Leninsky-Komsomol reached the North Pole. 1970, USS Queenfish carried out an extensive undersea mapping survey of the Siberian continental shelf. 1971, HMS Dreadnought reached the North Pole. USS Gurnard conducted 3 polar exercises. 1976 in which Charlton Heston boarded it. 1984 joint operations with USS Pintado. And in 1990 joint exercises with USS Seahorse. http://website.sbcook.com/ Gurnard/ For the history of the USS Gurnard and polar operations, May 6, 1986, USS Ray, USS Archerfish and USS Hokebill meet and surface together at the geographic North Pole. First multi-submarine surfacing at the pole, May 19, 1987, HMS Superb joined USS Billfish and USS Sea Devil at the North Pole. The first time British and Americans met at the North Pole, March 2007, USS Alexandria participated in the joint U.S. Navy-Royal Navy Ice Exercise 2007, ICEX 2007, in the Arctic Ocean with the Trafalgar-class submarine HMS Tireless. March 2009, USS Annapolis took part in Ice Exercise 2009 to test submarine operability and war-fighting capability in Arctic conditions.
Technology. Submersion and trimming.
All surface ships, as well as surface submarines, are in a positively buoyant condition, weighing less than the volume of water they would displace if fully submerged. To submerge hydrostatically, the ship must have negative buoyancy either by increasing its own weight or decreasing its displacement of water. To control their weight, submarines have ballast tanks, which can hold varying amounts of water and air. For general submersion or surfacing, submarines use the forward and aft tanks, called main ballast tanks, or MBTs, which are filled with water to submerge or with air to surface. Submerged, MBTs generally remain flooded, which simplifies their design, and on many submarines these tanks are a section of interhull space. For more precise and quick control of depth, submarines use smaller depth control tanks, or DCTs, also called hard tanks, due to their ability to withstand high pressure. The amount of water in depth control tanks can be controlled to change depth or to maintain a constant depth as outside conditions, chiefly water density, change. Depth control tanks may be located either near the submarine's center of gravity, or separated along the submarine body to prevent affecting trim. When submerged, the water pressure on a submarine's hull can reach 4 per 580 psi, for steel submarines and up to 10 per 1,500 psi, for titanium submarines like K278 Comjamalettes, while interior pressure remains relatively unchanged. This difference results in hull compression, which decreases displacement. Water density also increases with depth, as the salinity and pressure are higher, but this incompletely compensates for hull compression, so buoyancy decreases as depth increases. A submerged submarine is in an unstable equilibrium, having a tendency to either fall or float to the surface. Keeping a constant depth requires continual operation of either the depth control tanks or control surfaces. Submarines in a neutral buoyancy condition are not intrinsically trim stable. To maintain desired trim, submarines use forward and aft trim tanks. Pumps can move water between these, changing weight distribution, creating a moment pointing the sub up or down. A similar system is sometimes used to maintain stability. The hydrostatic effect of variable ballast tanks is not the only way to control the submarine underwater. Hydrodynamic maneuvering is done by several surfaces, which can be moved to create hydrodynamic forces when a submarine moves at sufficient speed. The stern planes, located near the propeller and normally horizontal, serve the same purpose as the trim tanks, controlling the trim, and are commonly used, while other control surfaces may not be present on many submarines. The fairwater planes on the sail and or bow planes on the main body, both also horizontal, are closer to the center of gravity, and are used to control depth with less effect on the trim. When a submarine performs an emergency surfacing, all depth and trim methods are used simultaneously, together with propelling the boat upwards. Such surfacing is very quick, so the sub may even partially jump out of the water, potentially damaging submarine systems.
Hull. Overview.
Modern submarines are cigar-shaped. This design, visible in early submarines, see below, is sometimes called a teardrop hull. It reduces the hydrodynamic drag when submerged, but decreases the seakeeping capabilities and increases drag while surfaced. Since the limitations of the propulsion systems of early submarines forced them to operate surfaced most of the time, their hull designs were a compromise. Because of the slow submerged speeds of those subs, usually well below 10 carats, 18 km per hour, the increased drag for underwater travel was acceptable. Late in World War II, when technology allowed faster and longer submerged operation and increased aircraft surveillance forced submarines to stay submerged, hull designs became teardrop-shaped again to reduce drag and noise. On modern military submarines, the outer hull is covered with a layer of sound-absorbing rubber, or anechoic plating, to reduce detection. The occupied pressure hulls of deep-diving submarines such as DSV Alvin are spherical instead of cylindrical. This allows a more even distribution of stress at the great depth. A titanium frame is usually affixed to the pressure hull, providing attachment for ballast and trim systems, scientific instrumentation, battery packs, syntactic flotation foam, and lighting. A raised tower on top of a submarine accommodates the periscope and electronics masts, which can include radio, radar, electronic warfare, and other systems including the snorkel mast. In many early classes of submarines, see history, the control room, or con, was located inside this tower, which was known as the conning tower. Since then, the con has been located within the hull of the submarine, and the tower is now called the sail. The con is distinct from the bridge, a small open platform in the top of the sail, used for observation during surface operation. Bathtubs are related to conning towers but are used on smaller submarines. The bathtub is a metal cylinder surrounding the hatch that prevents waves from breaking directly into the cabin. It is needed because surface submarines have limited freeboard, that is, they lie low in the water. Bathtubs help prevent swamping the vessel.
Single and double hulls.
Modern submarines and submersibles, as well as the oldest ones, usually have a single hull. Large submarines generally have an additional hull or hull sections outside. This external hull, which actually forms the shape of submarine, is called the outer hull, casing in the Royal Navy, or light hull, as it does not have to withstand a pressure difference. Inside the outer hull there is a strong hull, or pressure hull, which withstands sea pressure and has normal atmospheric pressure inside. As early as World War I, it was realized that the optimal shape for withstanding pressure conflicted with the optimal shape for sea air keeping and minimal drag, and construction difficulties further complicated the problem. This was solved either by a compromise shape, or by using two hulls. Internal for holding pressure, and external for optimal shape. Until the end of World War II, most submarines had an additional partial cover on the top, bow and stern, built of thinner metal, which was flooded when submerged. Germany went further with the Type XXI, a general predecessor of modern submarines, in which the pressure hull was fully enclosed inside the light hull, but optimized for submerged navigation, unlike earlier designs that were optimized for surface operation. After World War II, approaches split. The Soviet Union changed its designs, basing them on German developments. All post-World War II heavy Soviet and Russian submarines are built with a double hull structure. American and most other Western submarines switched to a primarily single hull approach. They still have light hull sections in the bow and stern, which house main ballast tanks and provide a hydrodynamically optimized shape, but the main cylindrical hull section has only a single plating layer. The double hulls are being considered for future submarines in the United States to improve payload capacity, stealth and range.
Pressure hull.
The pressure hull is generally constructed of thick high-strength steel with a complex structure and high-strength reserve, and is separated with watertight bulkheads into several compartments. There are also examples of more than two hulls in a submarine, like the Typhoon class, which has two main pressure hulls and three smaller ones for control room, torpedoes and steering gear, with the missile launch system between the main hulls. the dive depth cannot be increased easily. Simply making the hull thicker increases the weight and requires reduction of onboard equipment weight, ultimately resulting in a bathyscaphe. This is acceptable for civilian research submersibles, but not military submarines. WWI submarines had hulls of carbon steel, with a 100-meter (330 feet) maximum depth. During WWII, high-strength alloyed steel was introduced, allowing 200-meter (660 feet) depths. High-strength alloy steel remains the primary material for submarines today, with 250-400-meter (820 to 1,310 feet) depths, which cannot be exceeded on a military submarine without design compromises. To exceed that limit, a few submarines were built with titanium hulls. Titanium can be stronger than steel, lighter, and is not ferromagnetic, important for stealth. Titanium submarines were built by the Soviet Union, which developed specialized high-strength alloys. It has produced several types of titanium submarines. Titanium alloys allow a major increase in depth, but other systems must be redesigned to cope, so test depth was limited to 1,000 meters, 3,300 feet, for the Soviet submarine K-278 Komsomolets, the deepest diving combat submarine. An Alpha-class submarine may have successfully operated at 1,300 meters, 4,300 feet, though continuous operation at such depths would produce excessive stress on many submarine systems. Titanium does not flex as readily as steel, and may become brittle during many dive cycles. Despite its benefits, the high cost of titanium construction led to the abandonment of titanium submarine construction as the Cold War ended. Deep-diving civilian submarines have used thick acrylic pressure hulls. The deepest deep submergence vehicle, DSV, to date is Trieste. On October 5, 1959, Trieste departed San Diego for Guam aboard the freighter Santa Maria to participate in Project Necton, a series of very deep dives in the Mariana Trench. On January 23, 1960, Trieste reached the ocean floor in the Challenger Deep, the deepest southern part of the Mariana Trench, carrying Jacques Piccard, son of Auguste, and Lieutenant Don Walsh, USN. This was the first time a vessel, manned or unmanned, had reached the deepest point in the Earth's oceans. The onboard systems indicated a depth of 11,521 meters, 37,799 feet, although this was later revised to 10,916 meters, 35,814 feet, and more accurate measurements made in 1995 have found the Challenger Deep slightly shallower, at 10,911 meters, 35,797 feet. Building a pressure hull is difficult, as it must withstand pressures at its required diving depth. When the hull is perfectly round in cross-section, the pressure is evenly distributed, and causes only hull compression. If the shape is not perfect, the hull is bent, with several points heavily strained. Inevitable minor deviations are resisted by stiffener rings, but even a 1-inch, 25 mm, deviation from roundness results in over 30% decrease of maximal hydrostatic load and consequently dive depth. The hull must therefore be constructed with high precision. All hull parts must be welded without defects, and all joints are checked multiple times with different methods, contributing to the high cost of modern submarines. For example, each Virginia-class attack submarine costs $2.6 billion, over $200,000 per ton of displacement.
Propulsion.
Originally, submarines were human-propelled. The first mechanically driven submarine was the 1863 French Plongeur, which used compressed air for propulsion. Anaerobic propulsion was first employed by the Spanish Ictinio II in 1864, which used a solution of zinc, manganese dioxide, and potassium chlorate to generate sufficient heat to power a steam engine, while also providing oxygen for the crew. A similar system was not employed again until 1940 when the German Navy tested a hydrogen peroxide-based system, the Walter turbine, on the experimental V-80 submarine and later on the naval U-791 and Type 17 submarines. Until the advent of nuclear marine propulsion, most 20th-century submarines used batteries for running underwater and gasoline, petrol, or diesel engines on the surface, and for battery recharging. Early submarines used gasoline, but this quickly gave way to kerosene, paraffin, then diesel, because of reduced flammability. Diesel-electric became the standard means of propulsion. The diesel or gasoline engine and the electric motor, separated by clutches, were initially on the same shaft driving the propeller. This allowed the engine to drive the electric motor as a generator to recharge the batteries and also propel the submarine. The clutch between the motor and the engine would be disengaged when the submarine dived, so that the motor could drive the propeller. The motor could have multiple armatures on the shaft, which could be electrically coupled in series for slow speed and in parallel for high speed. These connections were called group down and group up, respectively.
Electric transmission. Diesel-electric.
Early submarines used a direct mechanical connection between the engine and propeller, switching between diesel engines for surface running, and battery-driven electric motors for submerged propulsion. In 1928, the United States Navy's Bureau of Engineering proposed a diesel-electric transmission. Instead of driving the propeller directly while running on the surface, the submarine's diesel drove a generator that could either charge the submarine's batteries or drive the electric motor. This made electric motor speed independent of diesel engine speed, so the diesel could run at an optimum and non-critical speed. One or more diesel engines could be shut down for maintenance while the submarine continued to run on the remaining engine or battery power. The U.S. pioneered this concept in 1929, in the S-class submarines S-3, S-6, and S-7. The first production submarines with this system were the Porpoise class of the 1930s, and it was used on most subsequent U.S. diesel submarines through the 1960s. No other navy adopted the system before 1945, apart from the Royal Navy's U-class submarines, though some submarines of the Imperial Japanese Navy used separate diesel generators for low-speed running. Other advantages of such an arrangement were that a submarine could travel slowly with the engines at full power to recharge the batteries quickly, reducing time on the surface or on snorkel. It was then possible to isolate the noisy diesel engines from the pressure hull, making the submarine quieter. Additionally, diesel-electric transmissions were more compact.
Air-independent propulsion.
During World War II, German Type XXI submarines were designed to carry hydrogen peroxide for long-term, fast air-independent propulsion, but were ultimately built with very large batteries instead. At the end of the war, the British and Soviets experimented with hydrogen peroxide kerosene, paraffin, engines that could run surfaced and submerged. The results were not encouraging. Though the Soviet Union deployed a class of submarines with this engine type, codenamed Quebec by NATO, they were considered unsuccessful. The United States also used hydrogen peroxide in an experimental midget submarine, X-1. It was originally powered by a hydrogen peroxide diesel engine and battery system until an explosion of her hydrogen peroxide supply on May 20, 1957. X-1 was later converted to use diesel-electric drive. Today several navies use air-independent propulsion. Notably Sweden uses Stirling technology on the Gotland-class and Södermanland-class submarines. The Stirling engine is heated by burning diesel fuel with liquid oxygen from cryogenic tanks. A newer development in air-independent propulsion is hydrogen fuel cells, first used on the German Type 212 submarine, with 934 kilowatts or two 120 kilowatt cells, and soon to be used in the new Spanish S-80 class submarines.
Nuclear power.
Steam power was resurrected in the 1950s with a nuclear-powered steam turbine driving a generator. By eliminating the need for atmospheric oxygen, the length of time that a modern submarine could remain submerged was limited only by its food stores, as breathing air was recycled and fresh water distilled from seawater. More importantly, a nuclear submarine has unlimited range at top speed. This allows it to travel from its operating base to the combat zone in a much shorter time and makes it a far more difficult target for most anti-submarine weapons. Nuclear-powered submarines have a relatively small battery and diesel engine generator power plant for emergency use if the reactors must be shut down. Nuclear power is now used in all large submarines, but due to the high cost and large size of nuclear reactors, smaller submarines still use diesel-electric propulsion. The ratio of larger to smaller submarines depends on strategic needs. The U.S. Navy, French Navy, and the British Royal Navy operate only nuclear submarines, which is explained by the need for distant operations. Other major operators rely on a mix of nuclear submarines for strategic purposes and diesel-electric submarines for defense. Most fleets have no nuclear submarines, due to the limited availability of nuclear power and submarine technology. Diesel-electric submarines have a stealth advantage over their nuclear counterparts. Nuclear submarines generate noise from coolant pumps and turbo machinery needed to operate the reactor, even at low power levels. Some nuclear submarines such as the American Ohio class can operate with their reactor coolant pumps secured, making them quieter than electric subs. A conventional submarine operating on batteries is almost completely silent, the only noise coming from the shaft bearings, propeller, and flow noise around the hull, all of which stops when the sub hovers in mid-water to listen, leaving only the noise from crew activity. Commercial submarines usually rely only on batteries, since they never operate independently of a mothership. Several serious nuclear and radiation accidents have involved nuclear submarine mishaps. The Soviet submarine K-19 reactor accident in 1961 resulted in 8 deaths and more than 30 other people were overexposed to radiation. The Soviet submarine K-27 reactor accident in 1968 resulted in 9 fatalities and 83 other injuries. The Soviet submarine K-431 accident in 1985 resulted in 10 fatalities and 49 other people suffered radiation injuries.
Alternative propulsion.
Oil-fired steam turbines powered the British K-class submarines, built during World War I and later, to give them the surface speed to keep up with the battle fleet. The K-class subs were not very successful, however. Toward the end of the 20th century, some submarines, such as the British Vanguard class, began to be fitted with pump jet propulsors instead of propellers. Though these are heavier, more expensive, and less efficient than a propeller, they are significantly quieter, providing an important tactical advantage. Magneto-hydrodynamic drive, MHD, was portrayed as the operating principle behind the titular submarine's nearly silent propulsion system in the film adaptation of The Hunt for Red October. However, in the novel The Red October did not use MHD, but rather something more similar to the above-mentioned pump jet. Although experimental surface ships have used this system, speeds have been below expectations. In addition, the drive system can induce bubble formation, compromising stealth, and the low efficiency requires high-powered reactors. These factors make it unlikely for military usage.
Armament.
The success of the submarine is inextricably linked to the development of the torpedo, invented by Robert Whitehead in 1866. His invention is essentially the same now as it was 140 years ago. Only with self-propelled torpedoes could the submarine make the leap from novelty to a weapon of war. Until the perfection of the guided torpedo, multiple straight-running torpedoes were required to attack a target. With at most 20 to 25 torpedoes stored on board, the number of attacks was limited. To increase combat endurance, most World War I submarines functioned as submersible gunboats, using their deck guns against unarmed targets, and diving to escape and engage enemy warships. The importance of guns encouraged the development of the unsuccessful submarine cruisers such as the French Surcouf and the Royal Navy's X-1 and M-class submarines. With the arrival of anti-submarine warfare, ASW, aircraft, guns became more for defense than attack. A more practical method of increasing combat endurance was the external torpedo tube, loaded only in port. The ability of submarines to approach enemy harbors covertly led to their use as mine layers. Mine-laying submarines of World War I and World War II were specially built for that purpose. Modern submarine-laid mines, such as the British Mark V Stonefish and Mark VI Sea Urchin, can deploy via a submarine's torpedo tubes. After World War II, both the US and the USSR experimented with submarine-launched cruise missiles such as the SSBN-8 Regulus and P-5 Piatkowska. Such missiles required the submarine to surface to fire its missiles. They were the forerunners of modern submarine-launched cruise missiles, which can be fired from the torpedo tubes of submerged submarines, for example the US BGM-109 Tomahawk and Russian RPK-2 Vuga, and versions of surface-to-surface anti-ship missiles such as the Exocet and Harpoon, encapsulated for submarine launch. Ballistic missiles can also be fired from a submarine's torpedo tubes, for example missiles such as the anti-submarine Subrock. With internal volume as limited as ever and the desire to carry heavier warloads, the idea of the external launch tube was revived, usually for encapsulated missiles, with such tubes being placed between the internal pressure and outer streamlined hulls. The strategic mission of the SSBN-8 and the P-5 were taken up by submarine-launched ballistic missile, beginning with the U.S. Navy's Polaris missile, and subsequently the Poseidon and Trident missiles. Germany is working on the torpedo tube-launched short-range IDAS missile, which can be used against ASW helicopters, as well as surface ships and coastal targets.
Sensors.
A submarine can have a variety of sensors, depending on its missions. Modern military submarines rely almost entirely on a suite of passive and active sonars to find targets. Active sonar relies on an audible ping to generate echoes to reveal objects around the submarine. Active systems are rarely used, as doing so reveals the sub's presence. Passive sonar is a set of sensitive hydrophones set into the hull or trailed in a towed array, generally several hundred feet long. The towed array is the mainstay of NATO submarine detection systems, as it reduces the flow noise heard by operators. Hull-mounted sonar is employed to back up the towed array, and in confined waters where obstacles could foul a towed array. Submarines also carry radar equipment to detect surface ships and aircraft. Submarine captains are more likely to use radar detection gear than active radar to detect targets, as radar can be detected far beyond its own return range, revealing the submarine. Periscopes are rarely used, except for position fixes and to verify a contact's identity. Civilian submarines, such as the DSV Alvin or the Russian Mir submersibles, rely on small active sonar sets and viewing ports to navigate. The human eye cannot detect sunlight below about 300 feet, 91 m, underwater, so high-intensity lights are used to illuminate the viewing area.
Navigation.
Early submarines had few navigation aids, but modern subs have a variety of navigation systems. Modern military submarines use an inertial guidance system for navigation while submerged, but drift error unavoidably builds over time. To counter this, the crew occasionally uses the global positioning system to obtain an accurate position. The periscope, a retractable tube with a prism system that provides a view of the surface, is only used occasionally in modern submarines, since the visibility range is short. The Virginia-class and Astute-class submarines use photonics masts rather than hull-penetrating optical periscopes. These masts must still be deployed above the surface, and use electronic sensors for visible light, infrared, laser range finding, and electromagnetic surveillance. One benefit to hoisting the mast above the surface is that while the mast is above the water, the entire sub is still below the water and is much harder to detect visibly or by radar.
Communication.
Military submarines use several systems to communicate with distant command centers or other ships. One is VLF, very low frequency, radio, which can reach a submarine either on the surface or submerged to a fairly shallow depth, usually less than 250 feet, 76 m. ELF, extremely low frequency, can reach a submarine at much greater depths, but has a very low bandwidth and are generally used to call a submerged sub to a shallower depth where VLF signals can reach. A submarine also has the option of floating a long, buoyant wire antenna to a shallower depth, allowing VLF transmissions by a deeply submerged boat. By extending a radio mast, a submarine can also use a burst transmission technique. A burst transmission takes only a fraction of a second, minimizing a submarine's risk of detection. To communicate with other submarines, a system known as Gertrude is used. Gertrude is basically a sonar telephone. Voice communication from one submarine is transmitted by low-power speakers into the water, where it is detected by passive sonars on the receiving submarine. The range of this system is probably very short, and using it radiates sound into the water, which can be heard by the enemy. Civilian submarines can use similar, albeit less powerful systems to communicate with support ships or other submersibles in the area.
Crew.
A typical nuclear submarine has a crew of over 80. Non-nuclear boats typically have fewer than half as many. The conditions on a submarine can be difficult because crew members must work in isolation for long periods of time, without family contact. Submarines normally maintain radio silence to avoid detection. Operating a submarine is dangerous, even in peacetime, and many submarines have been lost in accidents.
Women.
Most navies prohibited women from serving on submarines, even after they had been permitted to serve on surface warships. The Royal Norwegian Navy became the first navy to allow female crew on its submarines in 1985. The Royal Danish Navy allowed female submariners in 1988. Others followed suit including the Swedish Navy, 1989, the Royal Australian Navy, 1998, the German Navy, 2001, and the Canadian Navy, 2002. In 1995, Solveig Krag of the Royal Norwegian Navy became the first female officer to assume command on a military submarine, HMS Cobham. On December 8, 2011, British Defence Secretary Philip Hammond announced that the UK's ban on women in submarines was to be lifted from 2013. Previously there were fears that women were more at risk from a buildup of carbon dioxide in the submarine. But a study showed no medical reason to exclude women, though pregnant women would still be excluded. Similar dangers to the pregnant woman and her fetus barred females from submarine service in Sweden 1983, when all other positions were made available for them in the Swedish Navy. Today, pregnant women are still not allowed to serve on submarines in Sweden. However, the policymakers thought that it was discriminatory with a general ban and demanded that females should be tried on their individual merits and have their suitability evaluated and compared to other candidates. Further, they noted that a female complying with such high demands is unlikely to become pregnant. In May 2014 it was announced that 3 women had become the UN's first female submariners. Women have served on U.S. Navy surface ships since 1993, and as of 2011 to 2012, began serving on submarines for the first time. Until presently, the Navy only allowed 3 exceptions to women being on board military submarines: female civilian technicians for a few days at most, women midshipmen on an overnight during summer training for Navy ROTC and Naval Academy, and family members for one-day dependent cruises. In 2009, senior officials, including then Secretary of the Navy Ray Mabus, Joint Chief of Staff Admiral Michael Mullen, and Chief of Naval Operations Admiral Gary Roofhead, began the process of finding a way to implement females on board submarines. In 2011, the first classes of female submarine officers graduated from Naval Submarine School's Submarine Officer Basic Course, SOBC, at the Naval Submarine Base New London. Additionally, more senior-ranking and experienced female supply officers from the surface warfare specialty attend SOBC as well, and proceed to Fleet Ballistic Missile, SSBN, and Guided Missile, SSGN, submarines along with the new female submarine line officers beginning in late 2011/early 2012. Both the U.S. and British navies operate nuclear-powered submarines that deploy for periods of 6 months or longer. Other navies that permit women to serve on submarines operate conventionally powered submarines, which deploy for much shorter periods, usually only for 1 or 2 months. Prior to the recent change by the U.S., no nation using nuclear submarines permitted women to serve on board. In 2012, the U.S. Navy announced that 2013 is the first year that women will serve on U.S. attack submarines. In 2013, U.S. Navy Secretary Ray Mabus said that the first women to join Virginia-class attack subs had been chosen. They were newly commissioned female officers scheduled to report to their subs in fiscal year 2015. On October 15, 2013, the U.S. Navy announced the 2 submarines, the USS Virginia and the USS Minnesota, would have female crew members by January 2015.
Life support systems.
With nuclear power or air-independent propulsion, submarines can remain submerged for months at a time. Conventional diesel submarines must periodically resurface or snorkel to recharge their batteries. Most modern military submarines generate breathing oxygen by electrolysis of water. Atmosphere control equipment includes a CO2 scrubber, which uses an absorbent to remove the gas from air and diffuse it into waste pumped overboard. A machine that uses a catalyst to convert carbon monoxide into carbon dioxide, removed by the CO2 scrubber, and bonds hydrogen produced from the ship's storage battery with oxygen in the atmosphere to produce water, is also used. An atmosphere monitoring system samples the air from different areas of the ship for nitrogen, oxygen, hydrogen, R12 and R114 refrigerants, carbon dioxide, carbon monoxide, and other gases. Poisonous gases are removed, and oxygen is replenished by use of an oxygen bank located in a main ballast tank. Some heavier submarines have 2 oxygen bleed stations, forward and aft. The oxygen in the air is sometimes kept a few % less than atmospheric concentration to reduce fire danger. Fresh water is produced by either an evaporator or a reverse osmosis unit. The primary use for fresh water is to provide feed water for the reactor and steam propulsion plants. It is also available for showers, sinks, cooking and cleaning once propulsion plant needs have been met. Seawater is used to flush toilets, and the resulting black water is stored in a sanitary tank until it is blown overboard using pressurized air or pumped overboard by using a special sanitary pump. The method for blowing sanitaries overboard is difficult to operate, and the German Type VIIC boat U-1206 was lost with casualties because of a mistake with the toilet. Water from showers and sinks is stored separately in grey water tanks, which are pumped overboard using the drain pump. Trash on modern large submarines is usually disposed of using a tube called a trash disposal unit, TDU, where it is compacted into a galvanized steel can. At the bottom of the TDU is a large ball valve. An ice plug is set on top of the ball valve to protect it, the cans atop the ice plug. The top breech door is shut, and the TDU is flooded and equalized with sea pressure, the ball valve is opened and the cans fall out assisted by scrap iron weights in the cans. The TDU is also flushed with seawater to ensure it is completely empty and the ball valve is clear before shutting the valve.
Abandoning the vessel.
In an emergency, submarines can transmit a signal to other ships. The crew can use submarine escape immersion equipment to abandon a submarine. The crew can prevent a lung injury from the pressure change known as pulmonary barotrauma by exhaling during the ascent. Following escape from a pressurized submarine, the crew is at risk of developing decompression sickness. An alternative escape means is via a deep submergence rescue vehicle that can dock onto the disabled submarine. Deep diving and specialty submarines may deviate significantly from this traditional layout. Submarines change the amount of water and air in their ballast tanks to decrease buoyancy for submerging or increase it for surfacing. Submarines have one of the widest ranges of types and capabilities of any vessel. They range from small autonomous examples and 1 or 2 person vessels that operate for a few hours, to vessels that can remain submerged for 6 months, such as the Russian Typhoon class, the biggest submarines ever built. Submarines can work at greater depths than are survivable or practical for human divers. Modern deep-diving submarines derive from the bathyscaphe, which in turn evolved from the diving bell.
History. Early submersibles.
The first submersible of whose construction we have reliable information was built in 1620 by Cornelius Drebbel, a Dutchman in the service of James I of England. It was created to the standards of the design outlined by English mathematician William Bourne. It was propelled by means of oars. The precise nature of the submarine type is a matter of some controversy. Some claim that it was merely a bell towed by a boat. By the mid-18th century, over a dozen patents for submarine submersible boats had been granted in England. In 1747, Nathaniel Symonds patented and built the first known working example of the use of a ballast tank for submersion. His design used leather bags that could fill with water to submerge the craft. A mechanism was used to twist the water out of the bags and cause the boat to resurface. In 1749 the Gentleman's Magazine reported that a similar design had initially been proposed by Giovanni Borelli in 1680. By this point of development, further improvement in design necessarily stagnated for over a century, until new industrial technologies for propulsion and stability could be applied. The first military submarine was the Turtle, 1775, a hand-powered acorn-shaped device designed by the American David Bushnell to accommodate a single person. It was the first verified submarine capable of independent underwater operation and movement, and the first to use screws for propulsion. In 1800, France built a Huvelt that led to the first practical steam-powered submarines, armed with torpedoes and ready for military use. The first was the Nordenfeldt I, a 56-ton, 19.5-meter, 64 feet, vessel similar to Garrett's ill-fated Resurgam, 1879, with a range of 240 kilometers, 150 miles, 130 nanometers, armed with a single torpedo, in 1885. Like Resurgam, Nordenfeldt I operated on the surface by steam, then shut down its engine to dive. While submerged, the submarine released pressure generated when the engine was running on the surface to provide propulsion for some distance underwater. Greece, fearful of the return of the Ottomans, purchased it. Nordenfeldt then built Nordenfeldt II, Abdul Hamid, in 1886 and Nordenfeldt III, Abdul Mesud, in 1887, a pair of 30-meter, 100 feet, submarines with twin torpedo tubes, for the Ottoman Navy. Abdul Hamid became the first submarine in history to fire a torpedo submerged. Nordenfeldt's efforts culminated in 1887 with Nordenfeldt IV, which had twin motors and twin torpedoes. It was sold to the Russians, but proved unstable, ran aground, and was scrapped. A reliable means of propulsion for the submerged vessel was only made possible in the 1880s with the advent of the necessary electric battery technology. The first electrically powered boats were built by James Franklin Waddington in England, Dupuy de Lome and Gustave Zede in France and Isaac Perel in Spain. Waddington's Porpoise was similar in size to the Resurgam and its propulsion system consisted of 45 accumulator cells with a capacity of 660 ampere-hours each. These were coupled in series to a motor driving a propeller at about 750 rpms, giving the ship a sustained speed of 8 miles per hour for at least 8 hours. The boat was armed with 2 externally mounted torpedoes as well as a mine torpedo that could be detonated electronically. Although the boat performed well at trials, Waddington was unable to attract further contracts and went bankrupt. The Spanish Peril submarine was launched in 1888, and had 3 Schwarzkopf torpedoes 14 in, 360 mm, and one man-powered submarine designed by American Robert Fulton, the Nautilus. The French eventually gave up on the experiment in 1804, as did the British when they later considered Fulton's submarine design. In 1864, the 4th year of the American Civil War, the Confederate Navy's H.L. Hunley became the first military submarine to successfully sink an enemy vessel. In the aftermath of its successful attack against an American Union ship, the Hunley also sank, possibly due to its being too close to its own exploding torpedo.
Mechanical power.
The first submarine not relying on human power for propulsion was the French Plongeur, diver, launched in 1863, and using compressed air at 180 psi, 1241 kilopascals. The first air-independent and combustion-powered submarine was the Ictinio II, designed by the Spanish intellectual, artist and engineer Narcí Manchurial. Launched in Barcelona in 1864, it was originally human-powered, but in 1867 Manchurial invented an air-independent engine to power it underwater. The 14 meters, 46 feet, long craft was designed for a crew of 2, performed dives of 30 m, 98 feet, and remained underwater for 2 hours. Both the Ictinio I and II were double-hulled vessels that solved pressure and buoyancy control problems that had troubled and limited the functionality of earlier submarines. The submarine became a potentially viable weapon with the development of the Whitehead torpedo, the first practical self-propelled or locomotive torpedo. The spar torpedo that had been developed earlier by the Confederate Navy was considered to be impracticable, as it was believed to have sunk both its intended target, and probably the H.L. Hunley, the submarine that deployed it. The Whitehead torpedo was designed in 1866 by British engineer Robert Whitehead. His mined ship was an 11-foot-long, 14-inch diameter torpedo propelled by compressed air and carried an explosive warhead. The device had a speed of 7 knots, 13 km per hour, and it could hit a target 700 yards, 640 m, away. Discussions between the English clergyman and inventor George Garrett and the Swedish industrialist Horsten Norden.
Submarine.
A submarine is a watercraft capable of independent operation underwater. It differs from a submersible, which has more limited underwater capability. The term most commonly refers to a large, crewed, autonomous vessel. It is also sometimes used historically or colloquially to refer to remotely operated vehicles and robots, as well as medium-sized or smaller vessels, such as the midget submarine and the wet sub. Used as an adjective in phrases such as submarine cable, submarine means under the sea. The noun submarine evolved as a shortened form of submarine boat. For reasons of naval tradition, submarines are usually referred to as boats rather than as ships, regardless of their size. Although experimental submarines had been built before, submarine design took off during the 19th century, and they were adopted by several navies. Submarines were first widely used during World War I, 1914 to 1918, and now figure in many large navies. Military usage includes attacking enemy surface ships, merchant and military, submarines, aircraft carrier protection, blockade running, ballistic missile submarines as part of a nuclear strike force, reconnaissance, conventional land attack, for example using a cruise missile, and covert insertion of special forces. Civilian uses for submarines include marine science, salvage, exploration and facility inspection maintenance. Submarines can also be modified to perform more specialized functions such as search and rescue missions or undersea cable repair. Submarines are also used in tourism, and for undersea archaeology. Most large submarines consist of a cylindrical body with hemispherical, and/or conical, ends and a vertical structure, usually located amidships, which houses communications and sensing devices as well as periscopes. In modern submarines, this structure is the sail in American usage, and fin in European usage. A conning tower was a feature of earlier designs, a separate pressure hull above the main body of the boat that allowed the use of shorter periscopes. There is a propeller, or pump jet, at the rear, and various hydrodynamic control fins. Small untorpedo tube in bow, newer systems, hull shape, propeller, and cruciform external controls anticipating much later designs. Peril was an all-electrical powered submarine. After 2 years of trials the project was scrapped by naval officialdom who cited, among other reasons, concerns over the range permitted by its batteries. The Gymnot was launched by the French Navy in the same year. Gymnot was also an electrically powered and fully functional military submarine. It completed over 2,000 successful dives using a 204-cell battery. Although the Gymnot was scrapped for its limited range, its side hydroplanes became the standard for future submarine designs.
The modern submarine.
Submarines were not put into service for any widespread or routine use by navies until the early 1900s. The turn of the century marked a pivotal time in submarine development, and a number of important technologies appeared. A number of nations built and used submarines. Diesel-electric propulsion became the dominant power system, and equipment such as the periscope became standardized. Countries conducted many experiments on effective tactics and weapons for submarines, which led to their large impact in World War I. The Irish inventor John Philip Holland built a model submarine in 1876 and a full-scale one in 1878, followed by a number of unsuccessful ones. In 1896 he designed the Holland Type 6 submarine. This vessel made use of internal combustion engine power on the surface and electric battery power for submerged operations. Launched on May 17, 1897 at Navy Lieutenant Lewis Nixon's Crescent Shipyard in Elizabeth, New Jersey, the Holland 6 was purchased by the United States Navy on April 11, 1900, becoming the United States Navy's first commissioned submarine and renamed USS Holland. Commissioned in June 1900. The French steam and electric naval employed the now typical double-hull design, with a pressure hull inside the outer shell. These 200-ton ships had a range of over 100 miles, 160 kilometers, underwater. The French submarine Aigrette in 1904 further improved the concept by